Hello, this is Monika Sommerhalter again. In this video, I'm showing you how to analyze your data from the polyphenol oxidase activity assays. In this experiment, you recorded how the absorbance at 480 nanometer increases over time in a cuvette in which you pipetted crude banana extract, buffer, and the substrate, dopamine. You conducted several assays, and the volume of the crude extract was varied, but none of the other ingredients changed in concentration. The distilled water is balancing out the different volumes of the crude banana extract so that you always have 2 milliliter of final assay volume in your cuvette. The first step of the analysis is to convert these absorbance increase values per minute in international units of enzyme activity, or in other words, how many micromole dopamine were converted into dopamine chrome per minute. So micromole per minute is the final unit for enzyme activity. So here I can write PPO activity and then as a unit micromole per minute, which is the same as an international unit. The formula for the conversion is to take the absorbance change per time interval and divide that with the molar absorptivity value of the aminochrome, or 3,300 in units of 1 over molarity times 1 over centimeter. Then the 1 over centimeter will cancel out with the 1 centimeter cuvette path length, but you still need to consider the total volume of the assay, and the total volume is always 2 milliliter. But here we need to use liter and not milliliter, so I'm going to multiply with 0.002. And then to get micromole and not mole, I'm also going to multiply with a factor of 10 to the power of 6 to convert from mole to micromole. So if I now pull down this formula, I can double check. And I'm always using the absorbance per minute data and then applying the very same formula. The number of digits are too many. So I'm going in this direction here. The absorbance per minute slopes are often provided with 4 digits, but that's in the end also too many digits because the accuracy is also hampered by the accuracy of your pipettes, the titration. So in the end, we need to trim down to 2 or 3 digits for our very final result, maybe showing 3 digits, but only 2 digits at most will be significant. Now, what you see here are several activity values already in the correct units, but we are interested in figuring out how does the PPO activity change in this experiment as we use different volumes of the banana extract. Here all volumes are given in microliter. To make the final plot, I think I'll prefer milliliter because if I get a slope where the banana volume extract is on the x-axis, if I divide by a smaller number, I'll get higher numbers in the end, or with less leading zeros. So for convenience, I just write volume of crude banana extract, and the unit I want is milliliter. So I'm taking all the values from the banana extract and I'm dividing by 1000. Then I can pull down and get all the banana extract volumes in milliliter that were used in this experiment. To get a visual, I will insert a graph. So insert, and I'm choosing a scatter plot to get real XY data pairs of the individual measurements that I took. And I'm selecting the data right here with the data selection tool, and I'm only going to do one data series. So my X values are these volumes of crude extract that were used, and my Y values will be the PPO activity units. It's always important to provide axis titles, because else nobody else will know what is displayed on this graph. So the axis titles for the x-axis title, it's the volume of the crude banana extract, and actually it was the 10-fold diluted banana extract. In units of milliliter. I need to correct this here, volume of on the y-axis, I have the PPO activity in micromole per minute for international units. And I actually don't want to see all these zeros. So in the number, the way the number is displayed, I only need maybe 2 decimal places and not 4. I'm not too interested here in a chart title because it's only this one graph, and later in a report it's better to have a figure caption and not a chart title. What's important for this graph is to realize that as you increase the volume of the crude banana extract from one assay to the next, you get higher and higher PPO activity values because it's the crude banana extract that contains the polyphenol oxidase. So it's a linear relationship. And you can already imagine the trend line fitting very well through these data points. The question is, should this trend line go through 0? Because after all, if there's no banana extract, there's no PPO enzyme, so there shouldn't be any enzyme activity. Now, one thing to consider, though, is that even without the enzyme, dopamine and oxygen can still react with one another. So in your measurements, you probably have a data point with 0 milliliter or 0 microliter of crude banana extract, and you can confirm that there is maybe some slight activity, but not much. So because of these considerations that there is this background reaction, I'm not going to force the data curve through 0. So as I select the data, and for the trend line, I want to see all the options for this trend line so that I can be in control. I would like a linear trend line. And I'm not going to set the intercept to 0. I will inspect the value that I get. But I want to see the equation on the chart and display the R-square value on the chart. The closer R-square, or the correlation coefficient, is to 1, the better the fit between the individual data points and your linear curve. So 0.9824 is not perfect, but it's actually decent for this type of experiment. Then the slope will be of great significance for us because the slope in words means how does the PPO activity increase per milliliter of crude banana extract? The units will be then micromole over minute or milliliter. So 1 milliliter of banana extract, therefore, can catalyze the conversion of 0.9633 micromole dopamine in the time interval of 1 minute. 0.012 is close to 0, but not exactly 0. So there is some background reaction or overall shift to my data. If you want to see how this curve intersects or where it intersects, you can go backward by a small step, for example, 0.01 steps, to see where that curve intersects. But for the axis options, then I still want to start my axis at 0. And with that, your main part of the analysis is already complete. Crucial data are the slope. I can also use a slope function. So the known y values are the activity values, and the known x values are these. With respect to the number of significant digits, I'm going to trim it all the way down to displaying 3, but only 2 at most would be significant. And the units of the slope will be micromole over minute per milliliter. So this data was collected with the 10-fold diluted extract. The last question that remains is, what happened to the undiluted banana pulp extract? So the undiluted banana pulp extract has a 10-fold higher activity because the dilution factor is 10. So ultimately, the really final result is that 1 milliliter of crude banana pulp extract as prepared in this course can facilitate the oxidation of 9.63 or 9.6 dopamine substrate molecules per minute. So 9.63 micromole dopamine per 1 minute are converted into dopachrome with the help of the enzyme polyphenol oxidase that is present in the undiluted banana pulp extract. So have a good day, and this was the end of this video on the analysis of polyphenol oxidase activity.